times 315 divided by 12.2, and you get 263 ATM, millimeters of mercury. A. Okay. Same type of problem. This problem is almost identical. You're going to now convert 5 grams to SO2. So that's grams per mole is 64 to 1. Okay. Carbon dioxide is 5.0 grams also. Molar mass is 44 to 1. So 5 divided by 64 is 0.078 moles of SO2. 5 divided by 44 is 0.11. It's only 2 sig figs. So moles of CO2. And then I'm going to go back to PV equals nRT. So you want the total pressure. So you're going to add the 2 moles together, and you end up getting, when you add them, I'm just going to round that off to 8.19 moles total, because it would be 0.188, which rounds off to 0.19 if you do your sig figs correctly. Okay, so pressure equals the volume. That 750 milliliters, I have to convert that to liters, so I'm going to divide it by 1,000. So it's 0.75 liters. So I'm going to divide it by 0.75 liters because V ends up on the bottom. Okay, the moles is 0.19 moles. The R, they want atmospheres, so I'm going to use 0.0821. And then the temperature is 50 degrees. So temperature is 50 plus 273 is 323. Okay. So I got times 323. Okay. So doing all that work, 0.19 times 0.0821 times 323 divided by 0.75. The trick here was to make sure that you convert your volume from milliliters to liters, because that's what your R is in. That's why I always look at the units of R's. My answer I'm getting is 6.7. I would only look for 2 sig figs in this, ATMs. So really the 6.78 should just be 6.7. Okay, couple theory problems. Ready for that. Kinetic molecular theory. Constant random motion, that's the biggest tenet of kinetic molecular theory. So A is true. The average kinetic energy of the particle, now here the key word is directly to their centigrade temperature. It's not directly related, it's the square. If you look at the equation for URMS, now it's a square root relationship, the square of it. Attractive and repulsive forces between particles are stronger than between the particles of the walls. That is false. That is false. So I got my answer already. Inelastic, no, it should be elastic. So all these are not true, and the only one that's true is A. You should know. You should just, as a standard, know the basis, the tenets of kinetic molecular theory. Kinetic molecular theory predicts that pressure rises as the temperature of the gas increases. Why? Okay, so this is pressure over temperature equals P2 over temperature. Professor Dave, on a video I have posted, does a good job of comparing all the gas laws to kinetic molecular theory. It's worth taking a look if you want to look at that Professor Dave video. Why does this happen? Because if I have a box with molecules in it, okay? And I'm going to assume that that box is at a constant volume. As they start going, as you increase the temperature, they start hitting the walls more often. So you have more frequent collisions with the walls. Why does it go down? Because you have less frequent, because it's going slower. Okay? And there's another thing here. KE equals 1/2 mv squared. And then you have the RMS speed equals the square root of 3RT over the molar mass. So as you increase the temperature, the speed goes up, but that increase in velocity gives you a higher temperature, a higher kinetic energy. So this is actually true also. The molecules are hitting more energetically. It's increasing the kinetic energy on the walls. So I would say E is true. Both of those things are true. Okay. According to kinetic molecular theory, the molecules of different gases at the same temperature always have the same average kinetic energy. And the key word is at the same temperature. Temperature is a measure of your average kinetic energy. Which one has the greatest effusion at the temperature? What you want to look at for rate of effusion, RMS speed is the square root of 3RT over the molar mass. Well, as the molar mass goes up, your velocity goes down. As your molar mass goes down, your velocity increases. So it all has to do with the molar mass. Okay? So the greatest rate of diffusion would be the smallest molar mass. So if I just go down and do the molar masses, ammonia is 17 grams per mole, methane 16 grams per mole, argon is 40 grams per mole, HBr is like 80.1 or 80.9 grams per mole, and HCl is 36.5 grams per mole. So the greatest rate of diffusion would be the lightest, CH4. Fresh fish, easy question, okay? And then we get to our last problems we're going to get to. Missing problems now. On the back side of the last sheet I just did. It's always embarrassing when you're missing a sheet. There it is. On video. That's why staples are a good thing. Alright, here we go. Our last problems. Our last problems are going to all be on Graham's law mainly. And Graham's law is the rate of A over the rate of B is inversely proportional. So rate, the molar mass of A goes on the bottom, the molar mass of B goes on the top. So that's an inverse proportionality. Okay? So I want to compare the rate of effusion of, and it says FH, which really should be HF, to HBr. Hydrofluoric acid is roughly 20 grams per mole. HBr is 80.9 grams per mole. So I'm going to use this equation and I'm going to just plug in that the rate, I'll put the hydrofluoric acid on top, that's the faster one. I'll put the HBr on bottom. The heavier one is slower. Well, the heavier one ends up on top, 80.9 divided by 20. And then roughly, if I just looked at this, 80 divided by 20 is the square root of 4. So it's going to be about 2 times. So HBr is going to be out 2 times faster, and you actually get 2.01. The answer is C. Okay, put them in order in their increasing speed. Again, molar masses. Helium is 4, oxygen is 32, CO2 is 44, just looking at quick molar masses, N2 is 28. Okay, so it wants increasing speed. Okay, So the slowest one goes first. So it's CO2, and then what's faster than CO2 is oxygen. What's faster than oxygen is nitrogen. And increasing speed, the fastest one is helium. So we got C. Okay. Which now that these are your Graham's law problems down here. Which one would have the highest molecular speed at 25 degrees? Again, we want the lightest. I could have you calculate the URMS speed. It's really kind of easy. URMS, you always go 3RT over the molar mass. Things to know, the molar mass has to be in kilograms per mole, so you got to divide it by 1,000. Temperature is always in Kelvin, and the R you use is 8.314, and this is for energy, so we use joules and over mole per K. And technically a joule is a kilogram per meter squared per second squared. And that's where you get your velocity out of this. So I want the one that's highest, so it's going to be the lightest one. Real easy to do. Oxygen's 32, nitrogen's 28, 44 is CO2, 16 is methane, and all I can say about SO4 is it's probably really heavy. 32 plus 6 times 20 plus 120, so that one's like 152, just estimating. Well, the easy answer is it's methane at 16. Okay. A sample of O2 was found to diffuse a rate 3 times that of an unknown gas. So rate of O2, okay, is the rate of my unknown gas. That answer is 3. That's where they get 3 times. So that ratio equals 3. That's equal to the square root of their molar masses. So I know that the molar mass of oxygen goes on the bottom, and the molar mass of my unknown gas goes on top. Well, I know the molar mass of oxygen, so the molar mass of oxygen is 32. The molar mass of the gas is unknown, and this equals 3. Now I'm just going to apply a little bit of something called algebra. Okay, to get rid of the square root, I'm going to square both sides. So my answer becomes the molar mass of my unknown of x divided by 32 equals 9, 3 squared. And the answer is 9 times 32. So that answer, I'm doing it in my head, 9 times it is 8, and 9 times 3 is 27. So I got 288 grams per mole A. That is a Graham's law problem for finding unknown molar masses. A mixture is of carbon dioxide and unknown gas is allowed to diffuse in a container. The carbon is 1 times 2 as long, so it's slower. Okay, so when I look at this, I'm going to say that the rate of the unknown gas, man, I don't like that 1.2 times fine, as long. I guess I can say the rate of the unknown gas is 1.25 times as fast as the rate of carbon dioxide. The problem is always to know which one to put on top. The answer is, if you ever get a molar mass that's fractional, you put it in wrong. Your molar masses always have to be greater than 1. There's no molar mass that's fractional. Okay, so we got oxygen on top. I'm going to just plug in 32 for oxygen because I know it's 32. The unknown gas is going to be molar mass of x. Okay, I'm going to square both sides to solve for the denominator. So I end up with 1.25 squared is 1.56 equals 32 divided by the molar mass of x. Now, I can't solve for a variable in the denominator, so I'm going to multiply both sides by the molar mass of x. I'm going to divide each side by 1.56. That gets molar mass of x on the top. So in essence, I just flip them, top, bottom. And the answer should be 32 divided by 1.56. So what I got is I got roughly 20 grams per mole. Okay, chlorine is 71. I'm going to compare their actual molar masses. CO is going to be 12 plus 16, so CO is 30. 36. H2 is 2. And SO2 is 64. And I got a problem in that I came out with 20, so I'll think about this one for a second. The carbon dioxide's slower, so this is 44. So it has to be less than 44. I guess in my answer, I might just look at CO. Maybe I did some wrong math. 60, yeah, maybe the fact that CO is not 30. 16 plus 12. 28. Kind of late, so if I go 32 divided by 28 and take the square root of that, it's 1.07, so it's not CO2. I'll check HCl. HCl is heavier. I'm just going to leave this one. I have a problem with this, and I'm not sure what it is, so I'll just leave that away. I'll leave this one alone. Real gases behave most like ideal gases. Well, you want minimal interactions, and you could just think of real life conditions in a gas. When is a gas more like a gas? At high temperature, low temperature? Well, at low temperature, gases start attracting to each other and they freeze, or they become a liquid. So low temperature is not ideal conditions. Okay, that's what happens on different planets at low temperatures. You'll have oceans of carbon dioxide or oceans of oxygen or nitrogen. So we want high temperature. The pressure conditions we want are low. You want low interaction. So high pressure, again, would make a gas liquefy. If you ever look at a propane tank, it's inside, it's a liquid. Or a Bic lighter, if you have a clear lighter, you can see the liquid inside it. But as soon as you turn the button and it goes under low pressure. So our answer to B is, the answer to 29 is B. And I'll have to figure out what went wrong with 28. All right, we're done.